You know, as a land-grant university, we've always been about responding to the needs of our constituents, the country, the state. And nuclear engineering has a long history at NC State of being one of the originators of a nuclear engineering curriculum. But as important today is when we think about the need for clean energy and we think about climate change and the implications for clean energy for the future, nuclear engineering is as important as ever. The diversity of our program here in terms of what our scientists and engineers do and how they apply their skills in nuclear engineering to problems like health, and even using technology around plasma to work with our colleagues in the life sciences. It's just phenomenal. So we're very, very proud of our program.
We have a number of such projects which are in different areas, which is very important, as the Chancellor mentioned, diverse applications. And I would like to mention first the nuclear power and nuclear energy use, especially for advanced reactors. And right now, the focus of Department of Energy is on the small modular reactor and microreactor development. And our teams, we have two teams involved with Advanced Reactor Demonstration Program. There are two 7-year projects which just start, and we are only university involved in the two. The Department of Energy awarded two, and we are only university involved in that, and we are involved in one of the projects for microreactor. Also, we have very exciting projects in plasma science and engineering, ranging from application to medicine to treat certain diseases with Dr. Stephen Shannon, and also with Dr. Katerina Stapelman in applying to biological sciences and developing certain fertilized products, which is very exciting because this is really true multidisciplinary research. We have also very exciting project in nuclear materials, radiation detection, and many others. But the basic here message is that we are partnering with the industry and the national authorities and the government, and we are offering many different aspects of research and learning to our students which serve our community.
Constantine, one of the things that makes me so proud of your leadership and our faculty is we continue to grow our nuclear engineering program at NC State. And I think back, and we all stand on the shoulders of giants. And to think back that 70 years ago, people at this university had the vision to create a nuclear engineering program and curriculum around nuclear engineering, right, but to be the first university in the country to develop a non-governmental reactor on our campus for research. It just says that our forefathers and mothers had tremendous vision for the future, and it's great to see the impact that we continue to have, whether it's the safety of nuclear engineering, the detection of radiation and monitoring of radiation. Our department is in all of these critical areas for the future of nuclear science. It's been a gem for the university for over 70 years. My first message is really to thank them for not only celebrating this important field of science, but also celebrating NC State. Our history, as we've said repeatedly, is deep, and to have the atomic energy folks recognize what we do and to celebrate it means the world to us, and to highlight our strong history. So we're grateful, and grateful for all their work around the world to ensure that nuclear energy continues to be part of our solution and continues to be part of a clean energy solution and is done so safely.
My name is Louis Martin-Vega. I'm the Dean of the College of Engineering at NC State, and I'm delighted to be here to share with you my perspectives on the history of our nuclear engineering department, as well as the great promise it has in the future. At our university at NC State, we have a motto, which is think and do. And our faculty members and students work hand in hand to try to really deal with problems that we have that are vexing societal problems, not just from the basic science perspective, but also from the applications perspective. The development of solutions that benefit the health and well-being of our country and drive economic prosperity is a key part of this. And this applies perfectly, not only to our college in general, but certainly to our Department of Nuclear Engineering. The history of nuclear engineering is a very long and cherished history. It starts with one of my dean predecessors many years ago, Dean J. Harold Lampe. And he was the one that really made a very bold decision at that time to establish what was then the first research reactor on a university campus in our country, and we believe in the world, and the first nuclear engineering curriculum. With that start and that commitment, the program in nuclear engineering really started to develop and grew into what was a world-class program in this area. But like a lot of growth, there's sort of bumps and pauses along the way. And there were certain moments in time where, in fact, the nuclear engineering department and the field of nuclear engineering had a lot of challenges. Specifically around the year 2006, our nuclear engineering program, as nuclear engineering around the country was at a crossroads. Federal funding for research and programs in nuclear engineering were not really very abundant. Enrollment of students in nuclear engineering was actually quite low. There was still a lot of work getting out of the issues associated with things like the 3 Mile Island and debacle and other things like that, and even the concept of nuclear in general. And this is where decisions needed to be made. However, the fact that we had this commitment, we had a reactor on our campus where other campuses were closing their reactors. We had the integrity of a nuclear engineering program, whereas other programs were merging nuclear engineering with mechanical and others, really brought us to our advisory board. And I was able to come in, or I was part of the dean's operation at that time, came in as a dean of engineering, and we sat down with the members of the Nuclear Engineering Advisory Board. And they were the ones that gave us confidence and trust that in fact there were better days ahead, that it was really important to think about continuity of the program. So rather than just staying status quo, there were decisions that were made at that time that said, we're going to invest more in this program. There were only 8 faculty members in the department at that time. Well, we said, we're going to invest in 3 more faculty members over the next 3 years. But because of the relationships we had with national labs that were very strong, they were able to help us with joint appointments. In a few years, the critical mass had grown to about 14 faculty members. And lo and behold, at the federal level, a lot of other things started to happen. Dr. Stephen Chu became the Secretary of Energy, and with him, a real push to expand the efforts of national labs in the world of nuclear energy. Well, sometimes you have to be a little lucky. You have to be a little lucky in the sense that you position yourself for something that comes down that does provide a lot more support. And that's what started happening. Oak Ridge National Lab in particular led an effort for next generation nuclear reactor research. NC State, because of its critical mass in nuclear engineering, was chosen as the lead university in that effort. And that became the program known as CASTLE, which is the next generation nuclear reactor research. From that, many other things started to happen, and we continue to invest in the program to where today the faculty size is upwards of 23 faculty members. And it is clearly one of the most preeminent nuclear engineering programs in the country and in the world, ranked number 3 by US News report in the graduate program, something that we're extremely proud of. So it is clearly a preeminent program, but it was because there was a lot of work, a lot of commitment, and underlying that, outstanding quality faculty and leadership. Dr. Paul Terinsky led the department for many years and became a treasured advisor to the federal government in the area of nuclear energy. We were able to attract Yusri Azmi, who had a background at Oak Ridge National Labs, from Penn State to be head of the department. He drove it through the CASTLE stage and then another center called CNEC in nuclear nonproliferation. And then Dr. Ivanov, Konstantin Ivanov, joined us from Penn State as well. And he has taken the department to even higher levels with all of the work in the international sphere. The nuclear engineering department at NC State is one of the jewels of our university and certainly of our college. Again, nothing like this happens overnight. This was a result of many years of effort. We're talking almost 7 decades of commitment in this space that was made. And the folks that have been able to come and grow this department are proud of that heritage and of that legacy. Last but not least is the fact that even though we're talking about nuclear engineering, this department has played a catalyst role in interdisciplinary education and research across our campus. Many of our efforts are done together with people in the material science areas, other engineering areas, areas in the arts and sciences, and even in the humanities and social sciences in the areas of nuclear non-proliferation. The other thing that this department is doing is that it knows what great challenges and national challenges are. And in areas like nuclear non-proliferation, we're talking about National Academy of Engineering grand challenges where the department is truly a national and world leader. Needless to say, I'm extremely proud of the nuclear engineering department in our College of Engineering at NC State, of its history, but also of the tremendous promise for the future going forward. When you have a leader in a field of nuclear engineering like we have at NC State, only good things are going to come out of this into the future, because it is in fact this department and the few departments like it around the world that are driving the future of nuclear energy and the solution of many of our energy problems worldwide. It is abundantly clear that the future of our planet depends upon our ability to be able to harness the energy resources and needs that we have to serve a growing population, but in ways that are not destructive to our environment and our own survivability on this planet. Even though people oftentimes talk a great deal about renewable energy sources, part of the understanding here needs to be, and this is why we're so invested in nuclear engineering here at NC State, is that nuclear energy is a major part of this portfolio. We know that there's no silver bullet to this equation, but that nuclear energy, in fact, is a very key part of the portfolio, of an energy portfolio that will allow us to move forward in ways that we will continue to survive and be sustainable on our planet. And investments in this area need to be looked at in those terms, not simply in terms of moving an industry or the nuclear energy industry forward, but really finding a way to assure that we will be sustainable and continue to be able to survive on this planet. The main message of the Think and Do is the fact that, you know, we do basic research, but we also do as much work to transfer it to real life applications, right? And so nuclear engineering, in fact, has both of those components, because nuclear science is very much basic science and basic research ingrained in physics more than anything else. But it's the nuclear engineering piece of it that translates it into the societal needs and demands. Literally, in this case, you know, the energy sources that we need to be able to move our infrastructure forward. So that, I think, is you know, nuclear engineering encompasses the full brand of Think and Do in that regard. Thank you again for the opportunity to comment on what I consider to be clearly one of the jewels of our university. We're delighted that you're showcasing this department in your conference, and we invite you to come and visit at some future moment when it may be possible. We would very much like to show not only the department off, but everything that we're doing at our university. Thank you very much.
NC State University is located in Raleigh, the capital of North Carolina and a major southeastern city, only a few hours from the mountains, the coast, and the nation's capital, Washington, D.C. It's a vibrant city filled with arts and culture, natural beauty, great food, and southern charm. The area is also a fast-growing hub for technology and innovation, where top researchers and companies are solving the world's big problems in engineering and beyond. NC State is right in the middle of it all. We're a leading public research university with a long, rich history that helps us move boldly toward a better future. Here, more than 36,000 graduate and undergraduate students across many disciplines work together with expert faculty and top industry partners to think and do in new and exciting ways. Every day, we're researching, learning, building, growing, collaborating, and helping society thrive. And we have fun while we do it. What can you think and do at NC State? Anything.
My name is Ayman Houari. I am Professor of Nuclear Engineering and Director of the Nuclear Reactor Program at North Carolina State University. We are standing here in the control room of the PULSTAR reactor. The PULSTAR is a 1 megawatt thermal power nuclear reactor facility. It was built in 1972, went critical at that time, and it's been in operation since then, almost 50 years of age for the PULSTAR. The PULSTAR is used for various activities, including supporting nuclear engineering classes, doing research using neutron and radiation beams, and also serving all kinds of users from the community and the industry, and also research organizations and government organizations by providing radiation facilities and radiation diagnostic facilities. What you see here is the control console of the PULSTAR reactor. This is where our operators actually, on a day-to-day basis, monitor and operate the reactor, take it to different powers in order for the users to be given the type of radiation environments that they need and seek. The PULSTAR is a reactor that is fueled with uranium-235 fuel that is in a UO2 form and enriched to about 4% or 6% in U-235 weight ratio. Also, it is cooled by light water, moderated by light water, and it's an open pool reactor facility where the core sits in a light water pool about 25 feet depth. The reactor itself is somewhat unique in that the moderator to fuel ratio of this reactor is almost 1, which really gives us a neutron environment where the thermal neutrons actually peak on the edges of the core, facilitating the type of utilization that we do in the PULSTAR. The reactor is controlled by different control rods, and we can see here on the console the indicators for these control rods. The rods are made out of an alloy of cadmium and silver and indium, and this allows the operators to manipulate the power of the reactor and to make it reach a certain operational condition. We have an actively cooled core in that we have water being pumped in the core in order to make the core always stay at safe temperatures. The reactor has a primary cooling system connected to a secondary cooling system, and then eventually the heat is released to the environment. The core has several irradiation locations, like these standing pipes, where we can insert samples and irradiate them for different purposes. We also have the ability to introduce samples quickly and swiftly and remove them from the core through a rabbit tube system that allows us to pneumatically move those samples in and out of the core. We're also able to build facilities around the core over here for irradiation purposes. This reactor is also flexible in utilization because we can, as I said, manipulate the working conditions of the core in order to demonstrate various aspects of reactor operations. To give you an idea of the different facilities that we have established around the core of the reactor, and as you can see, this is the core again with the tube structures that I have discussed. This is a view of all of these instruments. We have instruments that can do neutron scattering on samples in order to study the structure of these samples at the micro and nanoscales. We have instruments that can do neutron imaging and radiography in order to see the internals of larger samples and, for example, examine them for any kind of defects and damage. And we have an instrument that is quite unique that is able of generating positive electrons. These are the positrons that interact with the samples and give us an idea of the defect structure in these samples. because many times when samples are manufactured, you might have actual atoms that are removed from their positions and have defects in the samples that control the properties of the sample. We are now building a new facility around our reactor, which specifically aims at testing advanced nuclear fuel materials, looking at microspheres of fuels. And these microspheres then are studies in order to see how they behave under fission conditions. We also have a facility to look at fundamental nuclear physics aspects or neutron physics aspects. This is the ultra-cold neutron facility, where we thermalize the neutrons to a very low energy at the nano electron volt scale, and then we are able to trap these neutrons and study their properties as free neutrons, such as the decay and lifetime of these neutrons. We are operating all these facilities simultaneously. Our staff scientists are able to operate, and also while other experiments and irradiations are taking place around the core itself. One of the unique capabilities that we have is the ability to use the educational aspects of our reactor through the internet. And we've introduced years ago the concept of the Internet Reactor Lab. In this capacity, the reactor console is rendered through a digital rendering and cast through the internet to students that are interested in understanding the operations of our reactor. In addition, those students are able to communicate with our operators through a video conferencing system. The console, as you can see it here, is rendered as a graphical user interface. And we also have graphical user interfaces for the different experiments that can be implemented through the Internet Reactor Lab. We are currently operating, and so all the readings that you see right now are actually real time. We have indicators of rod positions, powers, we have power meters, and we also have indicators related to our pool and temperatures. Through this capacity, we are able to introduce the students to various topics of reactor physics and operations. Experiments can be done to understand the criticality of the reactor and how to achieve critical conditions. Experiments can be done to understand the characteristics of the control rod by measurement of the rod worth of different control rods in the reactor. Experiments can also be done to understand the neutron field and the neutron flux distribution within the reactor core. And these are just examples of the various experiments that we can do. Working through the internet, we are able to share the capability of our reactor with different students around the country, different university campuses, and we've also developed the ability to do these internet lab exercises with the international community. And we actually implemented it and tested it in several countries, and in some cases we offered it to students in those countries as coursework that was taken for academic credit. We've worked with the IAEA to develop this capability. And we've also transferred this ability so that the IAEA can develop it with other countries.
This is our nuclear simulation lab at the Department of Nuclear Engineering. In this lab, we have this generic PWR simulator, which we use for our curriculum and research and outreach. So this GPWR simulator is a numerical model that models all the way from the reactor core to the turbine with the primary loop, secondary loop, and the safety systems. So it is a very important supplement to the simulation capabilities that we have in our program. In terms of teaching, we have incorporated this simulation lab, our simulator, into our nuclear reactor laboratory course, where we worked together with not only the PULSTAR reactor, which is the research reactor we have on campus, but also this numerical, full plant nuclear reactor simulator. And so students can have a full, complete experience of operation in a commercial nuclear power plant. We have been heavily using this GPWR simulator on our research side as well. More specifically, we have been using the simulator to generate a large amount of data to demonstrate the operation of commercial nuclear power plant. And those data is valuable for us to develop and train any machine learning models that could help us to determine the unseen pattern in the data, which will then be very useful for us to perform prognosis and diagnosis of the nuclear reactor systems.
My name is Ryan Scholl. I am currently a postdoc here at North Carolina State University, working under Dr. Jamel Kayomi. I've recently transitioned from a PhD student to a postdoc, and I'm able to work on a multitude of projects here. Basically, our research looks into the materials that are used inside the reactor as well as outside, and we want to understand how the effects of stress, corrosion, and irradiation are on the materials. We specifically look at the microstructure of these materials using electron microscopes over at the Analytical Instrument Facility on Centennial Campus. And we basically want to understand how the microstructure changes, because the microstructure governs the macroscopic properties such as the tensile strength and the ductility. Here we have our tensile and polishing lab, and here to present some of our work is Chris McRoby.
Hello, my name is Chris McRoby. I am an undergraduate student here at NC State. Here we have our Instron tensile testing machine. I work with Dr. Kayomi on this machine. The machine utilizes DIC, digital image correlation, to take pictures of our samples. Our samples are marked with these speckled patterns, and what this allows us to do is look at these speckled patterns as time goes on and see a local strain map, examine how the strain changes with respect to time. We're currently working on a project with INL, Idaho National Laboratory, where we're examining anisotropic materials such as zirconium, graphite, and other HCP materials, establishing baseline mechanical properties. We then plan on irradiating the samples and examining how these tensile properties change under an irradiation environment.
Our project involves developing new nickel-based oxide dispersion-strengthened nickel alloys for structural application in generation for nuclear reactors, specifically the molten salt reactor. ODS alloys are usually made out of steel, but we are trying to further develop their radiation resistance and corrosion resistance by using nickel as a base. This project is funded by the Department of Energy in collaboration with the Idaho National Laboratory, UC Berkeley, and Oxford University. So the nickel powder is mechanically processed at UC Berkeley. After that, here at NC State, we investigate the microstructure using electron microscopy, like TEM and SEM.
I have been working on thinning down some high entropy alloy samples of different chemical compositions to 100 micron and preparing them for transmission electron microscopy. Once these samples have been thinned down to 100 micron, we punch out 3mm discs from them, which are then electropolished until electron transparency, and then they are ready for transmission electron microscopy. These samples are then sent to the Argonne National Lab, where we use their IAEA microscope, which allows us to irradiate the samples with ions and allows us in situ to observe what is going on in the transmission electron microscope. This allows us to follow the microstructural evolutional changes in the alloys during irradiation. The goal of this project is to observe in high entropy alloys its radiation resistance in regard to its chemical composition and the elements involved, and what role each element plays in assisting or not assisting the high entropy alloys in their radiation resistance. So we have been looking at a particular class of high entropy alloys in the refractory section containing elements such as zirconium, niobium, tantalum, vanadium, and molybdenum, along with another system containing iron, chromium, nickel, and manganese. These samples have been prepared for us by the Idaho National Lab, which we are working in collaboration with, along with Bowling Green State University in Ohio, which is also working on observing positron annihilation spectroscopy in these same alloy samples.
I'm participating in potassium hydroxide project, which we are thinking of using potassium hydroxide to replace lithium hydroxide in pressurized water reactors. Currently, nuclear industry use lithium hydroxide to control water chemistry in pressurized water reactors. The lithium here is not a natural lithium. It should be enriched to a specific concentration. However, the cost for procuring lithium-7 has been increased significantly since 2015. And the potassium hydroxide is considered as a candidate since it's been used in Russian reactor for a long time. Also, potassium hydroxide doesn't need to be enriched, so it's economically favorable. Our collaborators include UC Berkeley, Pacific Northwest National Lab, and Electrical Power Research Institute. The objective of this work is to determine if it is possible to switch lithium hydroxide to potassium hydroxide without worsening the corrosion behavior of structural material in a reactor core. This is one of the samples we have. As you can see, it's very shiny because we did some sample preparation and we put this sample on this tree. And we will flip this head into the autoclave. And these two are static autoclave. They are very similar to real reactors, but just in a small scale. The temperature can go very high, around 325 degrees C, and the pressure is 2,500 psi. And there are two autoclaves, and because we want to separate different water chemistry solution. One would be lithium hydroxide, and the other is potassium hydroxide. And after exposing the sample into the autoclave for a certain time, the sample will be taken out, and we will do analysis such as TEM, SEM, or SIMS. We'll use electron microscope to observe what's the oxide formed on the materials. And we will use secondary ion mass spectrometry to study how the lithium or potassium cations penetrate into the oxide film to have better understanding for corrosion behavior in new water chemistry.
I'm here to present our recirculating loop autoclave, which allows us to simulate both boiling water reactor conditions and pressurized water conditions. And what we can do with this is actually monitor the water and chemistry at the same time as we're running our tests. We can add various dissolved chemicals such as lithium hydroxide, potassium hydroxide, or boric acid, as well as gaseous species, for example, such as hydrogen, to hydrogenate the water as you would see in a pressurized water condition. The other interesting feature of our loop autoclave that we have here is it also has a tensile machine attached to it, which allows us to add stress to our samples while we're running our tests, and that would be known as a stress corrosion cracking experiment. With that, we have a direct current potential drop system, which allows us to measure the potential drop over the course of the time and being able to relate that to the crack length so that we can actually get something like the crack growth rate, which is an important parameter. One of the projects that is associated with this is known as the silicon carbide project. Ever since Fukushima happened, we are always looking for accident-tolerant cladding. And one of the cladding candidates that we have is silicon carbide. The problem with silicon carbide is it corrodes a little faster than we like in boiling water conditions. So what we're looking to do is add on a coating either by physical vapor deposition or chemical vapor deposition, such as titanium nitride or zirconium nitride. And that project is just looking to see how fast our material corrodes and if we can improve it. So here we have one of our tensile apparatuses that actually allows us to do some in situ stress corrosion cracking over at Argonne National Lab's synchrotron source, which is known as the Advanced Photon Source. This project specifically was looking at canisters that we use for our spent nuclear fuel. And the problem with it is you could get a risk of crack propagation via chlorine-induced stress corrosion cracking for the canisters that are near the coastal of the United States. So what we were able to do is actually take cracked samples that we already pre-cracked and actually add in some salt and add some stress to it so that when we take it to Argonne National Lab, we can actually run our test and take what's known as X-ray tomographies over the course of the experiment. And what that allows us to do is basically track how far the crack is going and also the shape, which are both very important parameters.
Plasmas are used a lot for microelectronics manufacturing and for materials processing. And so we were doing a lot of work with companies like Samsung or Micron. We're doing work to basically make sure that you can make smaller and faster computer chips. And since that time, we've gone through this really fascinating transformation in our department as far as plasma science goes, where we continue to focus on our core knowledge base, which is still the materials processing and manufacturing, but have since then also moved into new areas. In fact, the lab that we're in right now is a lab that focuses on using plasmas for life sciences, using plasmas for things like medical treatments or treating biological materials. Professor Stoppelman is leading a multidisciplinary effort to use plasmas, among other technologies, for advanced agricultural applications, such as fertilizer production. So there is a ton of really exciting things that we never would have dreamed of 10 years ago that's going on right now. And then, of course, along with all that, we also have our collaborations with national labs where we do more of our traditional fusion energy work. So we've worked with Oak Ridge National Labs developing diagnostics for some of the monitoring plasma heating devices that they use for tokamaks. We were working with INL on expanding computational frameworks so we can do simulation work for fusion reactors. So there's lots of exciting things we're doing right now. So a bit of a catch-all, but definitely have our areas of expertise as well. First thing I want to make sure is I want to say that I'm obviously speaking on behalf of myself and also Professor Katerina Stoppelman, who's the other faculty member who works in the plasma lab. And also we have Dr. Alexander Bataler, who, although he doesn't have any experiments in this facility, his experiments are upstairs on the second and third floor. He's also collaborates with us quite a bit on plasma projects, but he works a lot with ultrafast spectroscopy and ultrafast lasers. So the students you'll be seeing today, first one is Nick Sponsel, who will talk a little bit about some of the work that's going on here in the Plasma Life Sciences Lab. We also have Carl Smith, who's doing some work funded by Samsung Electronics, trying to develop advanced plasma sources and advanced plasma technologies for microelectronics manufacturing. We have Josh Morsel, who's a graduate student working as part of a Department of Energy center that we're part of, where we're studying plasma interaction with complex interfaces. So broadly in the center, we focus on plasma interactions with nanoscale materials, plasma-enhanced catalysis, plasma interaction with liquids, which also has obviously a lot of overlap with some of the stuff that Professor Stoppelman's doing. So he's the graduate student who's supported through that center. And then finally, Naaman Bhatt, who's working on a project supported by a startup company here in the Triangle, Terra Medica. And we are developing plasma processes to purify chitosan powder for a host of medical applications. Everything from removal of toxins in biological systems to pharmaceutical drug delivery. So our role in it is actually taking the powder and purifying it to a level where you can use it for internal medicine, which is kind of exciting. We should be able to show over the course of this, also have some really nice demonstrations of some of the experiments that we're doing here as well.